Hello, friends. Good evening. We group three people are going to talk about fundamental forces, their properties, and the limitation of standard model, and why we need force carrier, basically. So, all the known forces in the universe can be divided into four fundamental forces. That is gravitational force, weak force, strong force, and electromagnetism. I think you all know that. So, going to talk about gravitational force. So, let's start with that. It was Isaac Newton who first proposed the idea of gravity. He explained it as kind of attraction between two objects, having mass, basically. But in his book, he said that he was not able to explain how two bodies at a distance interact with each other. But later on, Albert Einstein, through his theory of relativity, he explained that gravity is not a force, but it is a consequence of a large object or object bending space-time. So it works like that. Consider a large ball on a plain silk sheet. It should be thin, and place it in the middle. It will deform the cloth, and consider all the objects around it. It will fall into the middle. So that's how Albert Einstein explained the gravity. But yeah, he also there was a problem with the orbit of Mercury through his general relativity. He also explained the uh, the- uh, orbit of Mercury. According to standard model, interaction between two objects at a distance actually takes place due to their force carriers. Like something has to move from one place to the other object to interact between them. But for the gravitational force, we haven't found any like force carriers. So, but we have theorized how it should be, and Ashwara will explain it. Thank you.
So, gravitons are the postulated quanta and the force carriers of the gravitational field. They are theorized to be massless, neutrally charged particles that can travel at a speed of light, and it's similar to photons in an electromagnetic field. In order to combine Einstein's general relativity with quantum theory, we need to experimentally discover gravitons. And in case a particle is discovered that is massless and has an integer spin of 2, then that would be a graviton. But it's extremely hard to detect individual gravitons because gravity is a very weak force. Calculations suggest that even if we have a detector as heavy as Jupiter revolving and a neutron star, it would still struggle to detect a graviton. In quantum mechanics, waves can also be considered as vibrating. Sorry, particles can also be considered as vibrating waves. So, in this case, there can be more than one type of gravitons based on the strength of their vibration. Such particles are called Kaluza-Klein gravitons, and they can only exist if the idea of three dimensions can be extended to five dimensions. Now, let's talk about the next fundamental force, that is the electromagnetic force.
So, plunging down to the subatomic level, we can see how the atoms are made up of this nucleus in the center and which is surrounded by the electron cloud. Now, thinking about its structure, there is a positive charge to the nucleus, and the electrons have a negative charge, and these two obviously attract each other. Now, oppositely charged particles, what they do is they absorb each other's light, and this is what draws the particles together. Now, this phenomenon is known as electromagnetism, and this attractive force is the electromagnetic force. Now, this force acts as the glue which holds the matter in the universe together. Atoms would not hold themselves together if it wasn't for this force. Now, the universe without electromagnetism would make matter come apart at the seams and matter would dissolve in its absence. Now, think of it in this way. Imagine Thanos snapping his fingers and wiping out matter from the entire universe. This is exactly what would happen if the electromagnetic force was temporarily turned off. Okay. And we know that protons and electrons spit out short lived bursts of radiation in the form of photons.
So now let me shed some light on photons. Photons, often described as the discrete packets of energy, they are gauge bosons that are thought to be the carrier of electromagnetic field. They have a spin of one with two possibilities, that is left or right. They are chargeless particles. They have zero rest mass, and quantum numbers such as lepton number and baryon number for a photon is zero. Um, so they exhibit wave particle duality, and They obey Bose-Einstein statistics instead of Pauli exclusion principle. Existence of photons was proposed by Einstein in 1905 in his paper on photoelectric effect, but the term photon wasn't used until 1926. An electron jumping from a higher energy level to a lower energy level may emit a photon. Photons are also emitted when a particle and its antiparticle annihilates. So that was all about photon. Now I'll let Yuvan talk about the next force. Thank you.
So the next force is a strong force. So strong force, by its name itself, it is clear that it is the strongest of all the forces. So it is also stronger than electromagnetic force. So it overcomes the proton repulsion, and that is why the protons are held together inside the nucleus. So it is basically a fundamental interaction between the subatomic particles of matter in nature. So it binds quarks together in clusters to form some familiar subatomic particles such as protons and neutrons. Its range is very small, which is about 1 femtometer, which is 10 to power minus 15 meters. So it originates in a property known as a color. So this color has no connection with the real world meaning of color, which is visible sense. In somewhat, it is basically it is like electric charge, uh, uh, such as electric charge is a source of electromagnetism or electromagnetic force. Uh, as same, the color is the source of strong forces. That is the reason why leptons don't feel this strong force and quarks do. But wait, electromagnetic force has force carriers, right? So what about the strong forces? So my friend Krishna will continue with the strong forces, force carriers.
Okay. Gluons are the elemental particle that cause a strong interaction of quarks. Gluons are also indirectly responsible for binding of protons and neutrons in the nucleus. Technically, gluons are the vector gauge bosons that mediate the strong color charge interactions of quarks in the quantum electrodynamics. It has one as its speed. The gluons have two polarizations to be transferred. In quantum field theory, unbroken gauge variance requires that the gauge bosons have zero mass. The gluon has negative intrinsic parity and zero isospin. It also has its antiparticle. There are 8 types of gluons in quantum electrodynamics. The first direct experimental evidence of gluon was found in 1973 when 3 jet events were observed at electron-positron collider called as Petra at Daisy in Hamburg. Recently, quark-gluon plasma has been found at relativistic heavy ion collider. On weak forces, Manish will talk. Thank you.
Yeah, hello guys. Very good evening to all. Yeah, I'm going to talk about the weak forces. So in nuclear physics and particle physics, the weak interactions, which is also called the weak force, okay, is the mechanism of interaction between the subatomic particles, okay, that is responsible for radioactive decay of atoms. So what is the difference between strong and weak force? Strong forces are attractive forces between the protons and the neutrons that keep nucleus together, and weak nuclear force is responsible for radioactive decay of a certain nuclei. It governs decay of unstable subatomic particles such as mesons and initiates the nuclear fission reaction that fuels the state. Okay, so weak forces is carried out by W and Z bosons, which are nothing but the gauge bosons, okay, by emitting an electrically charged W boson. Okay. So the weak forces changes the flavor of quark, okay, which causes a proton to change into a neutron or vice versa. This is what triggers nuclear fusion and causes stars to burn. It is an attractive and repulsive in nature. Okay, this weak force is felt by the leptons as they don't feel a strong nuclear force. Electrically charged leptons interact via electromagnetic force. So finding W and Z boson led to a theory combining the electromagnetic force and the weak force into a unified electroweak force. So next discussion will be carried out by Sasireka, which is talking about W and Z bosons and chirality dependence. Thank you.
So, looking into the history of weak force carriers, in 1950s, scientists tested strong force and electromagnetic force and found that neither of them cared about the direction of the spin of the particles. However, in 1956, scientists tried to find out if weak force interactions cared about the distance direction of the spin of the particles. Hence, they conducted an experiment where they decayed cobalt nucleus into a nickel nucleus and an antineutrino and an electron. Since it's difficult to detect a neutrino, they observed in which direction the electron is flowing. They observed that the electron is always flowing in the direction opposite to the direction of the spin of the cobalt nucleus. Since the momentum is conserved, the neutrino should always move in the direction opposite to the electron. This implied that the weak force depends on specific spin configurations. So, what is spin? Simply put, spin is a property of an object which is rotating about its axis. So to know the direction of spin, right hand rule is used. So right hand rule says that to put your right hand on this rotation axis and then curl your fingers in the direction of the spinning, and then the right hand points to the direction of the spin. So if the direction of the spin is equal to the direction of the particle motion, it is called right-handed particle, and then if not, it is called left-handed particle. In the experiments, all the neutrinos were found to be right-handed and the antineutrinos were found to be left-handed. Since neutrinos are observed only via weak force, we can say that weak force only interacts with right-handed neutrinos and left-handed antineutrinos. So coming into weak force carriers, there are three particles which mediate these weak forces. There are W plus, W minus, and Z0 bosons. W plus and W minus have a positive and negative charge of +1, and Z0 boson is electrically a neutral particle. Among all the bosons, only these bosons have mass. The mass of W particle is about 80 giga electron volt per c square, and the mass of Z particle is about 91 giga electron volt per c square. There are two interactions in which these particles are exchanged. One of the interaction is charged current interaction, which is mediated by W boson, and the other interaction is neutral current interaction, which is mediated by Z boson. The two W bosons are known as the mediators of neutrino emission and absorption, whereas the Z boson mediates the transfer of momentum, spin, and energy. So, since we saw about all the fundamental forces and their force carriers, now let us see what is the need for these force carriers.
Thank you, Shashireka. I'm Chaitanya, and I'm here to talk about the need for force carriers. We have talked about bosons. Now let's see the need for it. This is just part of the mechanics of quantum field theory, which is what we get when we integrate standard quantum mechanics with special relativity. Particles is really a misnomer. In quantum field theory, particles are patterns of excitation in space-time filling fields. The basic reason is that the theory does not allow action at a distance. If something here is going to affect something there, then something has to travel between here and there to mediate that effect. The wave patterns which have been observed are what we call force carrier particles. Now, Sagnik is going to continue on Higgs boson and its properties. Thank you.
Thank you, Chaitanya. Hello, everyone. I will be talking about the Higgs boson and its property. All the known force fields have teeny vibrations because of the intrinsic fuzziness of quantum mechanics. But those are vibration around some average value, which is typically zero. Larger vibrations appear to us as a particle. The Higgs boson, the particle discovered at LHC on July 4, 2012, is a vibration in the Higgs field. If we think Higgs field as a water in a pond, and if we throw a stone in the water, we know what will happen. Ripples will be formed. So we can say ripples are the analogous to the Higgs boson. Now, what are its properties? Higgs boson is the only scalar boson, which means it has zero spin. It has zero electric charge and color charge. Higgs boson is its own antiparticle. Standard model does not accurately predict the mass of the Higgs boson.
Okay, so before we conclude, there was a small error in what Shashi said. It is all neutrinos are left-handed and all anti-neutrinos are right-handed. So that's the end of Group T's jam session. Thank you everyone for listening.